Hi, I'm Chloe Legendre, and today I'm going to be talking about learning to estimate environmental lighting. I'm presenting today on behalf of a large project team within Google Daydream, many of whom are also giving other tutorial sessions today. So we're in this session about how to capture and render high-quality digital humans. But for realistic rendering, we don't just need the virtual human assets, we also need to understand the lighting in the scene. So I'm going to be talking about how to bring realistic, high-quality lighting used for sophisticated visual effects to real-time mobile augmented reality applications, despite having very little information about the lighting in the scene. And because we're missing information, we're going to show how to do this using machine learning. So we're all familiar with augmented reality. We can think of this as any attempt to blend rendered content with real-world imagery, whether using a mobile phone, as shown here, or some kind of AR see-through display, such as the Microsoft HoloLens. In this example of Niantic's Pokemon Go, the virtual content is the rendered Pikachu, while the real-world imagery is the live camera feed captured with the cell phone. Now, I'm an avid Pokemon Go player myself. Here I've captured these two screen recordings. One is outside in partial shade with some sun, and one is indoors in a very orangey lighting. Now, despite being in very different scenes, both are lit and rendered in the same way. And we can look at a couple of other examples too. This can give us a picture of the state of AR lighting today. In both of these shots, the left in my condo and the other in a conference room, there's a strong light source coming from the window at the right. But Pikachu's shadow and overall shading make it look like there's just one single light source coming from above. And so the lighting on the virtual Pikachu isn't very consistent with that of the rest of the scene, which is just one strong visual cue that prevents us from really believing that these images are real. Now, for comparison with the state of the art from visual effects, here's a shot from the 2019 film Detective Pikachu, with this virtual Pikachu again in a scene with a bright window on the right. But in this case, we can see that the lighting on the Pikachu looks just about correct. We can see that the right side of the Pikachu is brightly lit, while the left side is in shadow, and we even see realistic reflections in his eyes. Now, most VFX shots like this one, that involve rendering synthetic objects into real-world scenes, rely on a photographed record of lighting that's measured in the real world. At SIGGRAPH in '98, Debevec introduced both the lighting measurement and rendering technique to enable realistic composites that blended both real and virtual imagery, as you can see in this shot. Now, because an object's appearance is the result of light arriving from a full sphere of lighting directions around it, this technique first involved measuring omnidirectional, real-world lighting using panoramic high dynamic range photography. In practice, this was achieved by photographing a mirror ball, which reflects light from all directions, using multiple exposures, and then radiometrically aligning the different shots. These multiple exposures were required because lighting in the real world is high dynamic range. Light sources can be orders of magnitude brighter than the rest of the scene. In the same work, images were shown of an object rendered with HDR lighting here on the left, compared with single image lighting here on the right, which is clearly wrong. And it still looks wrong if you just brighten the lighting. But if you can capture 360 imagery in HDR, you can very convincingly render synthetic objects into a real-world scene. Here are some virtual objects lit by several different photographed lighting environments. Because a series of photographs are used to represent the illumination, this technique came to be referred to as image-based lighting. The technique works well. It's used in most modern VFX-based films, but one drawback is that it requires photographing the real-world lighting well in advance of rendering. With this in mind, we can see that it's going to be totally impractical for mobile AR. We can't expect casual mobile phone users to go around photographing mirror spheres before an AR session, especially not in HDR. So let's look at what information we actually do have available during a typical AR session. At a minimum, we can assume that we have access to the live camera feed, one example shot shown here for a grassy path close to our Google office. But if we now look at the paired 360 environment, which I've shown here as a panorama, we can see that our cell phone camera with its limited field of view only sees about 6% of the incident lighting directions. And they're not even the most useful directions, because if we're going to render an object into this scene, we would have wished that we'd seen the light coming from above or from the front of the scene, which is actually light coming from behind the phone camera. And so that means that in the absence of our mirror ball image or panorama, we're looking at having to hallucinate 94% of the scene. But there actually is some hope, because it doesn't need to be this high resolution for accurate lighting, and objects in the cell phone image might be able to reveal some cues about the lighting in the scene. For instance, maybe an object casts a shadow. Now, the other thing worth noting is that the live camera feed is actually just a single exposure. It's usually compressed into an 8-bit range. And so that means that even for a few light sources that may be visible within the limited field of view, they're likely going to have a pixel value of 111, indicating that the sensor is fully saturated if the rest of the scene is well exposed. And that means that we're not going to be capturing their full intensity or color correctly in a single image. And again, that's just because we have this limited dynamic range in a single exposure. So then the question really boils down to, how do we get high dynamic range 360 lighting from a single exposure image with a limited field of view? Now, because so little information is actually available and our problem is massively under-constrained, it's a good candidate for a solution via machine learning. Gardner et al. Recently proposed a deep learning-based approach to regress from a limited field of view image to an HDR lighting environment. They first trained a neural network using a large database of single exposure panoramas and then fine-tuned with a small HDR panorama database of 2,100 indoor scenes. And although the method was limited to indoors, it did work well in some cases. However, the authors identified two key limitations to their technique. The first is that the output from the network often requires a global intensity scaling. Here on the left, the stuffed toy, which is virtual, is rendered with the ground truth lighting in the scene. The middle is rendered using the output from their network, and the right is after the output from their network is manually adjusted by an artist, just changing the intensity scaling. Additionally, their output HDR intensity map is a single channel image, and so they white balance it based on the average color of the input. And this can lead to color rendition errors, as you can see here for the rendered globe, which is more bluish in the ground truth rendering. A similar project tackled outdoor lighting estimation, also using a deep neural network. But this approach relied on regressing to sky model parameters, and so it's not going to be applicable for any indoor scene, or even for any outdoor scene that contains light sources other than the sun, for instance, a street lamp at night. However, both of these works nonetheless laid the groundwork for our current approach, where we're also going to use a deep neural network for the lighting estimation task. Instead of requiring a large number of HDR panoramas, which was a challenge for both of these approaches, we instead designed a mobile phone capture rig shown here, built by my colleague Jay Bush, allowing us to capture a large data set of cell phone videos that contain 3 different spheres with different reflectivities, which tell us all we need to know about the light in the scene. The mirror ball reflects 360 high-frequency lighting, but in a single exposure, bright light sources like the sun here will saturate the sensor, and so their color and intensity will be misrepresented. The diffuse gray ball, in contrast, reflects blurred, low-frequency lighting, but captures a relatively complete record of the total light in the scene, as well as its general directionality. And finally, the matte silver ball has a reflectance somewhere between these two extremes. With this rig, we're able to measure lighting information in a wide variety of both indoor and outdoor scenes. Here you can see some example videos from our training set. Once we've collected and processed these videos, we're now ready to train our model. The way that this works is that we train an encoder-decoder style convolutional neural network to directly estimate HDR lighting. The input is the low dynamic range background image captured by the phone with 3 spheres cropped out. Before training the network, we first photograph a reflectance field for each sphere. We do this by photographing the appearance of each sphere as lit by a tiny cone of the 360 lighting environment. This we capture using a light stage, as we've talked about earlier in this tutorial session. Now, because light is additive, we can linearly combine these images after scaling them to generate spheres lit by the predicted illumination. This rendering technique is called image-based relighting, and it's trivially differentiable as is required for gradient-based learning because it consists only of multiply and add operations. During training, we then minimize a rendering-based loss function where we compute the difference between the ground truth spheres from the training data and those that are rendered using the network estimated illumination. The idea behind using this rendering loss to train the network is that any material that we'd like to be able to render into the scene will include some diffuse, some sharp specular, and some rough specular reflections, and we want all kinds of these reflections to look realistic. Now, the last thing is that we also add an adversarial loss term for the rendered mirror balls to ensure plausible high-frequency illumination, because reconstruction losses alone often create overly blurred images. This loss term is implemented as an auxiliary convolutional neural network called a discriminator, whose only task is to learn how to predict real versus fake mirror ball images. The main network gets better and better at tricking the discriminator into thinking that its mirror balls are fake, or are real, rather than computer-generated. At this point now, we know how the network is trained and we understand how we capture data, so we're ready to see some results. On the left, we can see the input images for unseen indoor scenes, and on the right for a few outdoor scenes. The top rows show the ground truth spheres captured with the phone in the video, and then below, the bottom row shows the renderings that are produced using our lighting inference. Now, just to be clear, we're predicting the lighting that's being used to render the spheres rather than predicting the spheres themselves. And we can see the same now for outdoor scenes. Here's the ground truth, as well as the predicted renderings. Now, the mirror spheres here reflect plausible, high-frequency lighting, and the general directionality, intensity, and color balance have been learned, although we do still have some room for improvement. These aren't even the best results. These are actually images that represent the 25th, 50th, and 75th percentiles for our reconstruction or rendering loss. Now we can also look at some comparisons with the previous state-of-the-art techniques. Let's start by looking at some indoor scenes. Here are the input images, and then here again are the ground truth images, and these are followed by renderings produced using our lighting inference, and those using the previous state-of-the-art technique, which is Gardner et al. And for these examples, we clearly show a vast improvement. If we look at the lower left example of the green plant, we can see how the method of Gardner et al. Makes incorrect assumptions about the color of the light, incorrectly predicting that the green of the plant is the result of illumination rather than reflectance. The input image aspect ratio here differs because we wanted to have a fair comparison with the previous state-of-the-art technique. We can look similarly at a few outdoor scenes now. Here again are the input images and the ground truth images, followed by renderings that use our lighting inference and that of the previous state-of-the-art technique, in this case Holgiafroy et al. While we still do have some room for improvement, particularly as it pertains to hard shadow terminators, and that's why I've shown this example in the lower right, nonetheless, our method vastly outperforms the state-of-the-art here, both visually and quantitatively, although I haven't shown the numbers in this slide. We can further handle outdoor scenes with shade, outdoor scenes that have multiple or diffused light sources other than the sun, and we can also look at some now virtual object composites and then compare these with the ground truth lighting as well. To capture this kind of validation data, we built a multi-camera rig that allows us to take images with a cell phone and a DSLR at the same time. This allows us to get the ground truth background image from the phone, shown here, and the ground truth light probe by photographing a mirror sphere at multiple exposures. And now, because the two cameras are different in terms of their exposures and color balances, we also photograph a color chart to radiometrically align the mirror ball image to the color space of the cell phone camera to the best of our ability. This radiometric alignment is actually very tricky because the phone running in video mode employs all kinds of per-frame auto-exposure, white balancing, and tone mapping operations. At the same time, we're also able to photograph a real 3D printed object placed in the scene. Here, this bunny is actually a 3D print of the Stanford bunny that was again made by my colleague Jay Bush. So armed with this data, we can perform the following experiment. We can take a photo that serves as the clean plate or background, and then at the same time capture a photograph of the real 3D printed bunny that's placed in the scene. We can also capture the ground truth HDR lighting using our DSLR camera with multiple exposures, as I described earlier. And in this case now, I've rendered a diffuse bunny offline using the measured HDR lighting. This is labeled as the ground truth HDR IBL. Using now the same rendering settings, here I've rendered a diffuse bunny using our lighting inference, and also using that of the previous state of the art, which was Gardner et al. So clearly we're doing much better for this scene. And we can also now swap the reflectance function of the bunny. And so here we've got now a matte silver painted bunny who's a bit more reflective as well. And our hope here is that we would match both the real-world 3D print and the bunny that's rendered with the ground truth lighting. While we demonstrate improvements over the state-of-the-art techniques, we do have some room for further improvement ourselves. This has been a very limited subset of our results. Our full paper, which was presented at CVPR in 2019, includes about 100 scenes for the sphere renderings and 17 scenes, indoor and outdoor, that show the virtual bunnies rendered with the ground truth and inferred lighting. But these all so far have been offline renders. We also want to see this running in real time on a phone. And so since the acceptance of the publication at CVPR, some of my colleagues at Google and I have been working on making this available to augmented reality developers in Android's AR platform called AR Core. So this actually shipped as a product. It's called the Environmental HDR Lighting API. It was announced at Google I/O in 2019, and it's out now for AR Core Android developers to try. So next I'll show some scenes that include screenshots taken within an app that uses this new API built on top of the Unity game engine. And this app was developed by my colleague Jason Dargarian. So these are real-time renderings of a virtual rocket ship that's lit using our deep learning-based lighting estimates. And these are captured here as screenshots on an Android phone. Now, while the lighting here looks generally believable, and it does change as the scene changes, we do still have some work to do. For instance, in the second image from the left, we can see that the shadow direction, which is determined from the neural network output, looks correct, but as of right now, the API doesn't yet include the correct shadow ratio, and that's why some of the real-world shadows appear much darker than those that are cast by the virtual rocket ship. We can look at a few more examples in some different scenes. So the lighting does change as you move the rocket ship around to different environments, including indoor and outdoor scenes. And here are a few others. And finally, I'll show a few videos that are captured running in real time on the mobile phone. So here's a variety of different scenes. This one is kind of this dappled sunlight and shade outdoors. And then this one is the rocket ship being placed near a window. You can see the directional light has been learned correctly. This third one shows the rocket ship outside in direct sunlight next to a trash can that actually has a similar reflectance function as the rocket ship for comparison. And then finally, this is one that's indoors and kind of with a window coming from the right, light coming from the right, that is. So our HDR lighting API was also recently launched in Google's Scene Viewer, which is an app that's used to display interactive 3D models in AR from an Android app or browser. So now if you do a Google search for something and there's an associated 3D asset, you can see it rendered in your room in AR. For Christmas time, my colleague Alex Ma was playing with this Santa model near some non-denominational winter decorations in our Google office in Playa Vista. But because we're in a conference now that's specifically about rendering virtual humans, I fortunately have some examples from some of my other Google colleagues who have been using our lighting estimates to light some more realistic looking characters. This work was presented at SIGGRAPH Asia in 2019. The work was called The Relightable Volumetric Performance Capture of Humans with Realistic Relighting. So the captures here use the light stage type system that we've been talking about all morning, which is designed to capture a full body animated and relightable virtual human using some of the techniques we saw earlier. And then in this video, we've just lit them in AR using the lighting inference that's running from AR Core. On this last note, I want to summarize our contributions today. I've just presented our neural network-based approach for estimating high dynamic range 360 lighting from a single limited field of view image. The work was inspired by the desire to bring high-quality HDR image-based lighting to real-time mobile AR rendering. Our model is trained using only LDR input imagery, leveraging spheres with different reflectivities, yet it recovers the full dynamic range of lighting. Next, a lighting API built on top of our approach has been released to AR developers in Google's AR Core. Our approach outperformed the state of the art for both indoor and outdoor scenes, despite the fact that the other models were developed to handle only a single class of lighting. And on this more recent note, I'm actually very excited because since the publication of our work in 2019 at CVPR, several other research groups have been proposing new lighting estimation approaches, and indeed it's actually a very hot topic right now. So I wanted to highlight some of these here. Now, some of these works have even solved more challenging cases, such as trying to solve for spatially varying lighting from the scene, which our work did not address. But even considering these newer contributions, our method so far is the only one developed to handle arbitrary indoor and arbitrary outdoor illumination scenes. On that final note, I wanted to thank all of my collaborators, and I want to thank everyone for their time today.